Like many of the other topics in A-level chemistry, the rate equations topic contains a huge amount of calculations and procedures that you need to be able to know how to do, but it does also contain some key facts that you need to have memorised. The idea behind this video is that I've written a list of questions that are just pure factual recall based on the facts that you need to have memorised from the specification. There's a list of these questions in the description below, so you can download the worksheet, have a go at answering them, and then use this video to check that you have understood and remembered those key facts. In GCSE chemistry, we talked about the rate of a reaction as being the speed of that reaction, but now that you're doing A-levels, we need to be a bit more specific. So we say that the rate of a chemical reaction is the change in concentration of a substance per unit time. Concentration is always measured in moles per decimetre cubed, and then the rate is the change in that concentration per unit time. The unit time tends to be expressed as a second, so therefore the units for rate are moles per decimetre cubed per second. In the reaction A plus 2B reacts to form C, for every 1 mole of A that reacts, 2 moles of B must react with it, and this will produce 1 mole of C. If we have a graph that shows us how the concentration of a reagent changes over time, then we can identify what the rate of the reaction is at a particular time point by using tangents. So the first thing you need to do is to identify the time of interest on the x-axis, and then work out where that corresponds to on the curve. Then you're going to draw a tangent that needs to touch the curve at that time. As you hopefully know, your calculations are going to be most accurate when your tangent is as large as possible. Then you use that tangent as a surrogate for the curve and you calculate what the gradient of that tangent is. And you do this by looking at the change in y divided by the change in x. And when you have that gradient, that tells you what the rate of that reaction is. In rate equations, we show that we're talking about concentration by using square brackets. In order to work out whether a particular reaction is 0th or 1st or 2nd order with respect to a particular reactant, what we do is we change the concentration of that reactant and see how it affects the rate. So if we double the concentration and the rate doesn't change at all, then it's 0th order. If we double the concentration and that doubles the rate, then that's 1st order. And if we double the concentration and that quadruples the rate, in other words, 2 squared, then that means it's 2nd order with respect to that particular reactant. To calculate the overall order of a reaction, we just add together all of the partial orders. Your rate equations are all going to start with rate equals K. And here, because we're 1st order with respect to A, it's rate equals K and then A in square brackets with no power. And then we're 2nd order with respect to B, so therefore the B is squared, and C is not included in the rate equation because C would be raised to the power of 0 and anything to the power of 0 is 1, so there's no point in writing it in there. The only way that you can work out whether a reactant is 0th or 1st or 2nd order is experimentally. So you can't just look at the equation for a reaction and know what's going to be 1st or 2nd order. So what you need to do is plan a series of experiments in which only the concentration of the reactant that you're interested in is changing, and then, as we've discussed before, show that if you double the concentration of that reactant, does the rate not change, or does it also double, or does it also quadruple? There are a couple of different ways in which we can use the initial rate of a reaction in order to deduce the partial order of a reaction with respect to a particular reactant. The first one is only going to apply in a situation in which we can accurately monitor the concentration of that reactant throughout the course of the reaction. So this could be something where we've got a reactant that is very brightly coloured and it's gradually going to be used up in the reaction, in which case we might be able to use colorimetry. Or it could also apply if the reactant is going to affect the conductivity of a solution, and therefore as the conductivity changes we can use that to monitor the concentration. So if that is the case, then we can have a set of data that's plotted on a graph showing us how the concentration changes over the course of the experiment, and then we can take a tangent and calculate what the gradient of the graph is at t equals 0, and that will give you the initial rate. Alternatively, you might be able to use a clock reaction. So this could be something like the iodine clock or the sodium thiosulfate and hydrochloric acid reaction, where you form that sulfur precipitate, and it means that a cross that you're looking at on a piece of paper will gradually seem to disappear. Now, for either one of those clock reactions, what you can do is take the time that it takes for the reaction to finish and use the reciprocal of that time as a surrogate for rate. Now, the reason that we can do this is that we assume that it always takes the same amount of sulfur for the cross to disappear, or the same amount of iodine for the colour change to happen. And so because we know that we're always making the same amount of product, we can use 1 over T as a surrogate for rate because it's going to be directly proportional to the rate. So since we know that, we can plan a series of experiments in which we change the concentration of one reactant and see how does that affect the time taken for the reaction to finish. If a particular reaction is 0th order with respect to a reactant, then the concentration of that reactant doesn't impact the rate, and therefore you're going to have a horizontal graph. If it's 1st order with respect to that reactant, then your graph is going to be directly proportional. So as the concentration doubles, the rate doubles, and the graph will pass through the origin, and it will be a straight line graph. And then if it's 2nd order with respect to a particular reactant, you're going to get an exponential graph. So as the concentration doubles, the rate quadruples and it's going to curve upwards. If you're looking at concentration against time instead of against rate, what we're going to find is that for 0th order, the concentration doesn't affect the rate. So therefore, the gradient of the graph is just going to consistently slope downwards. It doesn't matter that the concentration is dropping, the reaction is not going to go any slower as a result. Then if you have a graph where we're 1st order with respect to that reactant, we're going to see this curve. So initially the reaction goes quite quickly, but then as the concentration drops, the rate of reaction also drops, and so the gradient of the graph becomes more shallow. And then for 2nd order, we see the same kind of overall shape, but it's just more extreme. This symbol here means directly proportional. In other words, as one thing doubles, the thing you're comparing it to also doubles. You might find a catalyst present in the rate equation, which wouldn't be in the chemical equation because it's not actually being used up, it's not making a new chemical, but it is affecting the rate of reaction. If a species isn't present in the rate equation, it's because it doesn't affect the rate of reaction. In other words, it's 0th order. K is the rate constant, so this is the number that allows us to actually give a numerical value for how fast is the rate of that reaction compared to the concentrations of the reactants in it. Once you know the value of K for a particular reaction, it's only going to change in response to a change in temperature. K has lots of different units, and to work out the units, we need to basically do a balancing act looking at the units for rate, which are going to be moles per decimeter cubed per second, and the units for the different concentrations, which are all moles per decimeter cubed, and basically working out what K needs to be in order to make the two sides of our equation balance. So here we've got rate as moles per decimeter cubed per second equal to K multiplied by those 3 sets of moles per decimeter cubed. So firstly we can do a little bit of cancelling, 1 set of moles per decimeter cubed on each side, and that leaves us with seconds to the -1 divided by moles per decimeter cubed squared. So firstly I could expand those brackets to get moles squared decimeters to the -6, and then rather than leaving this as a fraction, what I can do is take the reciprocal, and the way that I do that is by raising all of those powers to -1. So instead of 1 over moles squared, I can write moles to the -2, and instead of 1 over decimeters to the -6, I can just write decimeter 6. And even though mathematically the convention would be to put positive integers first, in chemistry we just keep things in the order they've always been. So we've always said moles per decimeter cubed, so we stick with moles before decimeters and those before second, even though we've got these negative powers in there. So for that first rate equation, we've got units of moles to the -2, decimeters to the 6, seconds to the -1. Then for my second rate equation, I'm going to have units of moles to the -1, decimeters cubed, seconds to the -1. So that second to the -1 is never changing, it's always per second. And then for our last one, we just have seconds to the -1. Your Maxwell-Boltzmann distribution should look something like this. So we've got energy on the x-axis and number of particles or frequency or something like that on the y-axis, and an activation energy marked. Now, if we then increase the temperature of this reaction, we're going to have a curve that has the same area underneath it because you've got the same total number of particles, but it's skewed to the right. So it's got a lower peak that's moved over towards the right-hand side. And what we can see there is that many more particles have an energy that is higher than the activation energy, and that's why it has such a dramatic impact on K and hence on the rate of reaction. The activation energy is the minimum energy that's required for particles to successfully react when they collide. The rate determining step is the slowest step in a multi-stage reaction mechanism, and we can identify this from the rate equation because the number of moles of every reactant that is required to get to end of the rate determining step will match the rate equation. So for instance, if we have a rate equation that is just rate equals K multiplied by the concentration of A squared, then we know that we're going to need 2 moles of A to get to the end of the rate determining step, and we're not going to need anything else. In the Arrhenius equation, K of course is our rate constant and A is our Arrhenius constant, which again is different for every single chemical reaction. E is the numerical value approximately equal to 2.72, but you should have a button on your calculator that will give you the exact value. And EA is the activation energy. R is the gas constant and T is the temperature. Now, as we've said, the units for K and also for A are going to vary by reaction, and they're going to be the same as each other, but they always take the form moles to the power of something, decimeters to the power of something, although that something might be 0, and then seconds to the -1. E doesn't have any units, it's just a number like pi. Activation energy can be in joules per mole or more commonly kilojoules per mole. So watch out for this one because often they're going to give it to you in kilojoules per mole, but in order to use it in the equation, it needs to match up with the other values that we've got. And the gas constant, of course, is in joules per mole per Kelvin. So we need it to be in joules per mole before you can use it together. And then temperature, of course, is in Kelvin. You know from GCSE maths that a straight line graph can be explained using the equation y equals mx plus c. So m is the value of the gradient and c is the value of the intercept. And one of the forms of the Arrhenius equation can match up with this. So we have ln k, the natural log of k, is equal to the negative value of the activation energy divided by the gas constant times temperature plus the negative logarithm of the Arrhenius constant. So in this equation, ln k is y. So in other words, ln k is going on our y-axis, and you're going to have negative numbers for this, so that's why my axes are a slightly funny way around. Then 1 over t is going to be our value for x. So on your x-axis you're going to have 1 divided by the temperature. And then that means that your gradient is whatever 1 over t is multiplied by. So the negative activation energy divided by the gas constant, and the natural log of A is going to be the intercept. So you graph your data on those axes that you've drawn, and then this will allow you to calculate what the gradient is. And the gradient, as we've just said, is minus EA over R. So therefore, if we want to get the activation energy on its own, you multiply both sides of that equation by R, and then you multiply both sides of that equation by -1, and we get activation energy is minus mR, and you know that R is the gas constant, is 8.31. Well done for getting to the end, and hopefully you're now feeling slightly more confident with some of the facts that you need to know for this rate equations topic. Now you're ready to move on to some calculations, and I've got lots of videos to help with those. If you have found this useful, then don't forget to like and subscribe for more A-level chemistry videos coming soon.